You know what question keeps me up at night? Not literally, because I value my sleep, but intellectually, philosophically, it's this. Can we move through time the way we move through space? Can we visit yesterday the way we visit Paris? Can we skip ahead to next Tuesday like flipping pages in a book? Time travel. Just saying those words feels like stepping into science fiction. But here's the thing. The physics, the actual equations that govern our universe, they don't say no. Not exactly. They don't slam the door in our face. What they do is open it just a crack and then show us all these impossible looking obstacles on the other side. Let me start with something that might surprise you. Einstein's general relativity, the theory that explains gravity as the curvature of space-time, actually allows for something called closed time-like curves. These are paths through space-time that loop back on themselves. Follow one of these paths and you could theoretically arrive at a point in your own past. Einstein himself wasn't thrilled about this. It made him uncomfortable. But the mathematics doesn't care about our comfort. The equations are what they are. The first person to really take this seriously was Kurt Gödel. You might know him as the mathematician who proved there are true things that can't be proven. Brilliant guy. In 1949, he gave Einstein a birthday present. Not socks or a tie. He gave him a solution to Einstein's field equations. A rotating universe where closed time-like curves exist everywhere. Einstein was troubled by it. But he couldn't find anything wrong with the math. It was valid. Disturbing, but valid. Now, this brings us to the paradoxes. The logical nightmares that make time travel seem impossible even when the math says it might work. The grandfather paradox. You probably heard of it. You build a time machine. You go back to before your parents were born, and you do something, anything, that prevents your grandparents from ever meeting. Maybe you save your grandfather from an accident. That's how he originally met your grandmother. Good deed. Right? Except now they never meet. Which means your parent is never born, which means you're never born. But if you're never born, you can't go back to prevent their meeting. So they do meet. So you are born. So you do go back. Round and round we go. It's a logical contradiction. A paradox in the truest sense. And physicists have been trying to solve this for decades. Trying to find ways around it. Trying to figure out what actually happens when you create one of these situations. One solution is beautifully simple. The universe just won't let you do it. This is called the Novikov self-consistency principle, named after Igor Novikov. The idea is that if you try to create a paradox, something will always stop you. Not some cosmic cop jumping out to arrest you, just the laws of physics conspiring, in a sense, to maintain consistency. You go back to shoot your grandfather. Your gun jams. You try again. You slip. You try again. You have a sudden change of heart. Something, anything, prevents the paradox. The timeline protects itself. There's actually been an experiment testing a version of this, not with actual time travel, we can't do that yet, but with photons and quantum mechanics. Researchers at the University of Queensland simulated a photon traveling back in time through a wormhole and interacting with its past self. What they found was fascinating. Quantum mechanics automatically adjusted the probability so no paradox occurred. The photon couldn't destroy its past self in a way that would prevent its future existence. Nature, it seems, has built-in safeguards against logical inconsistencies. But there's another solution, one that's even more mind-bending. The many worlds interpretation applied to time travel. This says that when you go back and change something, you don't actually alter your own past. You create a new timeline, a branching universe where events unfold differently. So you go back. You prevent your grandparents from meeting. But this happens in a new branch of reality. In your original timeline, the one you came from, you were still born. You still built the time machine. You still traveled back. But now there's another universe, a parallel one, where you were never born. Both exist. Both are real. You just can't go back to your original timeline anymore. This comes from quantum mechanics. From the work of Hugh Everett in the 1950 seconds. He proposed that every quantum measurement causes the universe to split into multiple branches, each representing a different possible outcome. Apply this to time travel, and you get a consistent picture. No paradoxes, just an ever-branching tree of timeline. You can visit the past, you can change things, but you're always creating new branches rather than altering your own history. David Deutsch at Oxford has developed this idea extensively. He's shown that if you combine many worlds with quantum mechanics, time travel becomes theoretically possible without paradoxes. You're not changing history, you're making new history. Now, how would you actually build a time machine? Because this is where things get really interesting. The most famous proposal is the wormhole, an Einstein-Rosen bridge, as it's technically called. Einstein and his colleague Nathan Rosen described this in 1935, though they didn't think of it as a time machine. A wormhole is basically a tunnel through space-time, a shortcut connecting two distant points. Imagine space-time as a flat sheet. Fold it so 2 points touch. A wormhole is the connection between those points. If you could create or find a wormhole, you could travel through it and emerge somewhere else almost instantaneously. But here's the clever part. Here's how it becomes a time machine. Take one end of the wormhole and accelerate it to near the speed of light. Time dilation kicks in. Time passes more slowly for the moving end. When you bring it back, the two ends of the wormhole are now at different times, different moments. Enter one end, and you emerge from the other end in the past. Not your distant past necessarily, but earlier than when you entered. Kip Thorne, Nobel Prize winner for his work on gravitational waves, studied this in the 1982nd. Carl Sagan was writing the novel Contact and asked Thorne for a scientifically plausible way to move his characters across vast distances. Thorne suggested wormholes, and that got him thinking seriously about their properties. He and his colleagues showed that while wormholes are permitted by general relativity, keeping them open requires exotic matter, matter with negative energy density. We've never seen such matter in large quantities, though quantum mechanics hints it might exist. The Casimir effect, for instance. You place two metal plates very close together in a vacuum. Quantum fluctuations create a pressure that pushes them together. The energy between the plates is negative compared to the surrounding space. It's a tiny effect, but it proves negative energy can exist. Scaling it up to keep a wormhole open, though, that's beyond us by many orders of magnitude. There are other proposals, rotating black holes, for instance. When a black hole spins, it drags space-time around with it. Inside a rotating black hole, the structure becomes incredibly complex. There might be paths that let you avoid the singularity and emerge at a different time. But the journey would tear you apart long before you experience any time travel. Spaghettification, we call it. The tidal forces would stretch you like pasta. Then there's the Tipler cylinder, an infinitely long cylinder of extremely dense matter rotating rapidly. The math shows that if you circle around it in the right way, you could travel into your own past. The problem? It requires infinite length and matter so dense that creating it is impossible with any foreseeable technology. It's more a mathematical curiosity than a practical proposal. Miguel Alcubierre proposed something interesting in 1994, the Alcubierre drive. Not exactly a time machine, but related. You contract space-time in front of a spacecraft and expand it behind, creating a wave of curved space-time that carries the ship along. The ship itself stays in a flat bubble. It doesn't experience acceleration. Because you're manipulating space-time, not moving through it, you could potentially travel faster than light. And if you can travel faster than light, you can arrive somewhere before light from your departure reaches it. Which means, in a sense, you're moving backward in time relative to that location. This also requires exotic matter, enormous quantities of it. Early calculations suggested you need more negative energy than exists in the observable universe. Later work reduced this somewhat, but it's still far beyond us. All these proposals share something. They're permitted by physics, but require conditions we can't create. It's like nature is saying, yes, time travel is possible, but I'm going to make it extraordinarily difficult. Stephen Hawking thought there might be a deeper principle at work. He proposed the chronology protection conjecture, the idea that the laws of physics prevent closed time-like curves from forming except maybe on microscopic scales. But he couldn't prove it. It remains a conjecture, a hypothesis waiting for a theory of quantum gravity to either confirm or refute. Speaking of quantum gravity, that's where we need answers. General relativity permits time travel under certain conditions. But it doesn't include quantum mechanics. And quantum mechanics has its own strange relationship with time. At the quantum level, particles exist in superpositions, multiple states simultaneously. Time in quantum mechanics is treated as an absolute parameter, not something that curves. When we eventually develop a complete theory unifying relativity and quantum mechanics, whether that's string theory or loop quantum gravity or something new, it will tell us definitively whether time travel is truly possible. It might say closed time-like curves can't exist in reality, that they're mathematical artifacts, or it might say they can exist but only under conditions so extreme we'll never access them. Let me talk about causality. Our entire understanding of the universe is built on cause and effect. You drop a glass, It falls, it shatters. The dropping causes the shattering. But with time travel, this sequence gets confused. An effect could precede its cause, or even cause itself. There's a thought experiment called the bootstrap paradox. You travel back in time and give Shakespeare the complete works of Shakespeare. He publishes them centuries later. You find them, admire them, and take them back to give to Shakespeare. Who wrote the plays? You didn't. You copied them. Shakespeare didn't. He received them from you. The information exists in a loop with no creator. It bootstrapped itself into existence. This reveals something profound about information. In our normal experience, every idea has a source. Someone composes a symphony. Someone discovers a theorem. But in a closed, time-like curve, information could exist without ever being created. That violates our intuition deeply. There's also the predestination paradox. Your actions in the past create the future you're trying to change. You travel back to prevent a disaster, but your presence causes it. You become part of the causal chain. It's self-fulfilling rather than self-contradictory, which makes it consistent with the Novikov principle. But it raises uncomfortable questions about free will. If you're destined to travel back and cause the event, did you ever have a choice? Now, there's fascinating research on time travel with quantum particles. Not people or spaceships, information and photon, quantum entanglement. Two particles connected so that measuring one instantly affects the other, no matter the distance. Einstein called this spooky action at a distance. Some interpretations suggest quantum mechanics might allow retrocausality, future events influencing past ones. Delayed choice experiments. A decision made after a photon passes through an apparatus seems to determine how it behaved before the choice was made. John Wheeler proposed these in the 1,970 seconds and 80 seconds. Variations have been performed. The results challenge our linear notion of cause and effect. Seth Lloyd at MIT proposed using quantum mechanics to resolve time travel paradoxes. When you try to create a paradox, the probability becomes zero. The universe doesn't forbid trying, but quantum mechanics ensures it always fails. The same structure that gives us superposition automatically prevents paradoxes. Researchers have simulated this with photons. These aren't actual time travel experiments, but they test the framework. And they find that quantum mechanics resolves paradoxes automatically. Let me tell you about time crystals. Not geological crystals, patterns that repeat in time rather than space. A regular crystal has structure repeating in space, atoms in a lattice. A time crystal has structure repeating in time, oscillating indefinitely without energy input. This seems to violate thermodynamics. But Frank Wilczek proposed they might exist in 2012. Several groups created them in 2016 and 2017. They exist. They don't give us time travel, but they show that time could be more structured than we thought. They hint at possibilities we haven't explored. The arrow of time. Why does time flow in one direction? Why do we remember the past but not the future? Why do eggs break but never reassemble? The laws of physics at the fundamental level are time symmetric. A movie of particles colliding looks the same backward or forward. But our experience isn't symmetric. The answer lies in entropy. Disorder. The second law of thermodynamics says entropy always increases. A broken egg has higher entropy than an intact one. More ways to be broken than whole. The universe moves from lower entropy to higher entropy. This gives us the arrow of time. But here's the puzzle. If entropy always increases, the past had lower entropy. At the Big Bang, the universe was in an extremely low entropy state. Why? Low entropy states are rare, improbable. Why did the universe start ordered? Roger Penrose proposed there must have been a constraint, something requiring smoothness. But we don't know why. If we could explain why the universe started with low entropy, we'd understand why time flows forward, why there's causality and memory. Some theories suggest time's arrow might be different in different regions, near black holes, in other universes. Time might flow differently. There's also the question of whether past and future exist. Presentism says only now is real. Eternalism says all moments are equally real. Past, present, and future exist in a four-dimensional block. If eternalism is correct, time travel is less paradoxical. Your past self already exists. Traveling to meet them isn't changing anything. The timeline already includes your arrival. But if presentism is correct, time travel becomes problematic. You'd be traveling to a past that no longer exists. Julian Barber proposes something radical. Time doesn't exist at all. What we call time is an illusion created by how we perceive static configurations. Each moment is separate. They don't flow. We perceive flow because memories create narrative, but there's no passing of time. If he's right, time travel is meaningless. You can't travel through something that doesn't exist. Let me talk about tachyons, hypothetical particles that travel faster than light. First proposed in the 1960 seconds. The math of relativity doesn't forbid faster than light particles. They'd have imaginary mass. And from their perspective, they'd move backward in time. If you could send signals with tachyons, you could communicate with your past, creating paradoxes. Most physicists suspect they don't exist. We've never detected one. It seems nature might forbid them precisely because they'd allow paradoxes. String theory has interesting things to say. Fundamental objects are vibrating strings, not point particles. The theory requires extra dimensions beyond our 3 spatial and 1-time dimension. In some versions, these extra dimensions could affect causality. Paths through higher dimensional space might be shortcuts through space-time. Arriving at your past, the math is complex. But string theory doesn't automatically forbid closed time-like curves. Loop quantum gravity takes a different approach. Space and time are quantized, made of discrete units, quantum foam at the smallest scales, the Planck length and Planck time. Below these scales, space and time break down. Time might emerge from something more fundamental. Carlo Rovelli, one of the founders, suggests time as we experience it isn't fundamental. It arises from our perspective. At the quantum gravity level, there might be no time at all, just relationships between quantum states. If true, time travel paradoxes might dissolve. They rely on a notion of time that only exists at large scales. Now, something practical. Observing the past without traveling to it. We do this all the time. When you look at a star, you see it as it was years ago. Light takes time to travel. Andromeda appears as it was 2.5 million years ago. Could we observe Earth's past? If you could travel faster than light, you could catch up with light that left Earth long ago. See, historical events. This requires faster than light travel, which we can't do. But it's a thought experiment showing how light creates a historical record spreading through space. The holographic principle suggests information in a volume is encoded on its boundary, from studying black holes. If correct, information about past events might be encoded on distant boundaries. Recovering it would require unimaginable technology, but it might not be impossible. Black holes present fascinating questions. When something falls into a black hole, time slows infinitely from our perspective. We never see it cross the horizon, but from the falling object's perspective, time passes normally. It crosses in finite time. Hawking showed black holes emit radiation. They evaporate, creating the information paradox. What happens to information that fell in? Recent work suggests information might be preserved in Hawking radiation, scrambled, or encoded on the event horizon, or stored in a remnant. Rotating black holes have complex interiors where time becomes tangled. Paths might exist for time travel. But tidal forces would be lethal. Cosmic strings, hypothetical one-dimensional defects in space-time, formed in the early universe, incredibly thin but massively dense. J. Richard Gott showed in 1991 that 2 cosmic strings passing at high speed could create closed time-like curves around them. This wouldn't require exotic matter, just the string's mass and motion. The catch? We don't know if cosmic strings exist. We've never detected one. The early universe might have been a place where time worked differently. At the Big Bang, space-time was in quantum superposition. Time, as we know it, might not have existed before the Planck epoch. Some models suggest the universe has no beginning in time. Time becomes space-like near what we call the Big Bang, like a sphere's surface. No edge, but finite. Asking what happened before the Big Bang is like asking what's north of the North Pole. The question doesn't make sense. If time emerged from something else, traveling backward might mean approaching where time ceases to have meaning. Now, experimental tests. We've confirmed time is relative. Different observers experience time at different rates. The Hafele-Keating experiment in 1971. Atomic clocks flew around the world on airliners. Compared to a stationary clock, the flying clocks measured different times. Nanosecond differences, exactly as Einstein predicted. This wasn't time travel, but it was time dilation. moving clocks experience time differently. Take this to extremes. Accelerate to near light speed, and you could travel thousands of years into Earth's future while aging only a few years. The twin paradox. One twin stays on Earth. The other travels at relativistic speed to a distant star and back. The traveling twin ages less. They've traveled to the future. GPS requires corrections for relativity. Satellites orbit at high speeds and in weaker gravity. Their clocks run differently. Without corrections, GPS would be off by kilometers. Particle accelerators provide dramatic confirmation. Muons created in the upper atmosphere should decay before reaching the ground. But we detect them because time is dilated. From our frame, their clocks run slow. We create muons in accelerators and watch them live longer. The faster we accelerate them, the longer they live from our perspective. Time genuinely depends on motion and gravity. This isn't theory, it's observation. Ronald Mallet at the University of Connecticut proposed using circulating laser beams to create a rotating cylinder of light. Could theoretically twist space-time enough for closed time-like curves. Energy requirements would be enormous, and questions remain about whether the effect would be strong enough. Mallet's motivation is personal. His father died young. He spent his career trying to find a way to send a message back, to warn his father, perhaps save him. Behind the abstract physics are human desires and sorrow. If time travel is possible and civilizations can become advanced enough, why don't we see time travelers from the future? One answer: it's impossible. Despite what relativity allows, some deeper principle forbids it. Another: time travelers exist but hide carefully, avoiding disrupting history. Or perhaps time travel is only possible to points after the time machine is built. You can't travel before the machine exists. So we wouldn't see travelers from our future until we build one. Hawking hosted a party for time travelers, announced it afterward. No one showed up. He took this as evidence time travel isn't possible. Though it's hardly conclusive, maybe no future travelers were interested. Maybe they attended but hid. Maybe conditions are so restrictive, casual visits are impossible. There's also the simulation hypothesis. If we're in a computer simulation, time travel might just be the simulators running the program backward. From inside, it would appear as time travel. From outside, just data manipulation. Now, retrocausality in quantum mechanics. The transactional interpretation, where quantum events involve waves traveling both forward and backward in time. When you measure a system, the measurement sends a wave backward to when the system was prepared. The interaction creates the outcome. It sounds bizarre, but it makes identical predictions to standard quantum mechanics. Delayed choice experiments seem to show retrocausality. You make a choice after a photon passes through an apparatus, yet the photon behaves as if it knew what you choose. It's not information traveling backward usefully, but it suggests the quantum world doesn't respect our temporal ordering. Yakir Aharonov developed the two-state vector formalism. A quantum system is described by both a state from the past and a state from the future. The present is determined by both. The quantum eraser experiment illustrates this. You set up interference patterns that appear or disappear based on whether information is available. You can erase or reveal information after photons have been detected. Looking at correlated data, it appears photons knew what you'd do in the future. You can't send information backward, but it challenges our intuition about time. These experiments reveal that time at the quantum level is stranger than everyday experience. They hint that in extreme conditions, time could behave in ways we can't imagine. Let me talk about consciousness and time. Our experience of time is bound to memory and anticipation. The past exists as memory. The future as imagination. The present moment is actually a construct. Your brain assembles it from sensory data arriving at different times. Vision takes longer to process than touch. Your brain synchronizes inputs to create the illusion of now. Studies show what we experience as now encompasses about 3 seconds. Your brain integrates information over this window. This is why music works, why we perceive melody. Notes separated by more than 3 seconds feel disconnected. Within that window, they flow. Time at the subjective level has granularity, texture, determined by neural processing. What would happen to subjective time near a black hole or through a wormhole? Would conscious experience stretch or compress? Would you feel time passing differently? These aren't just philosophical questions. If we achieve extreme time dilation, people will experience these conditions. Experiments with altered consciousness provide hints. Psychedelics make time seem to slow or speed. Hours feel like minutes, or vice versa. Neuroscientists find changes in brain connectivity that might explain distortions. The brain's internal clock can speed up or slow down by altering neural activity. This suggests subjective time is plastic, malleable. Dependent on brain state, perhaps time travel would be less jarring than we imagine. Your brain might adapt. Or perhaps you'd experience profound disorientation. The arrow of time in cosmology connects to deep questions. The early universe was extremely low entropy, hot, dense, uniform plasma. As it expanded and cooled, uniformity broke down. Matter clumped. Entropy increased. This creates the arrow of time. But why was initial entropy so low? A random configuration would be maximum entropy. Cold, diffuse particles. No structure. The fact our universe started low entropy requires explanation. Penrose proposed there might be a law constraining initial conditions. Others suggest multiverse, different regions with different initial conditions. We're in a low entropy region because only those allow complex structures. Selection effect, anthropic reasoning. We observe low initial entropy because we couldn't exist otherwise. If multiverse is correct, there might be regions where time runs backward, where entropy decreases. To inhabitants, time would flow opposite. But consciousness requires entropy increase. Creating memories, a mind running backward wouldn't be conscious in recognizable ways. The heat death. Far future, when entropy reaches maximum, nothing interesting happens. Time might continue, but no events mark its passage. Timeless. Penrose's conformal cyclic cosmology suggests heat death isn't the end. The universe passes through into a new phase, mathematically equivalent to another Big Bang. Time doesn't end. It recycles. The far future of one cycle becomes the Big Bang of the next. It's beautiful. Has observational predictions related to cosmic microwave background. Data is ambiguous so far. If he's right, time is eternal in cycles. Perhaps there are echoes of previous cycles we could detect. Time travel in fiction involves machines, flashing lights, spinning components. But real physics suggests it's about geometry, not machinery. You don't build a device that moves through time. You engineer space-time into a configuration permitting temporal loops. This is profoundly different. Most technology manipulates matter and energy. But manipulating space-time requires controlling massive energy with incredible precision, understanding quantum gravity well enough to avoid disasters. The Alcubierre drive illustrates this. You're not pushing a ship through space. You're contracting space in front and expanding behind, creating a bubble that surfs on space-time distortion. The ship doesn't move in its local frame. Space moves around it. This requires rethinking movement and distance. If you can manipulate space-time so precisely, you're approaching godlike capabilities. You could create regions where time flows at different rates. Pocket universes, bridges between distant cosmos parts, sculpting reality. This is metric engineering, subject of serious physics papers. Though practical challenges are immense, some speculate advanced civilizations might do this routinely, building structures out of space-time rather than matter. A Dyson sphere of curved space-time, collecting energy from vacuum fluctuations. A habitat where time flows slower inside, giving inhabitants more subjective time. Frank Tipler wrote about the omega point, a collapsing universe model where advanced civilizations engineer the far future for infinite computation. As the universe contracts unevenly, chaotic dynamics can be harnessed. Oscillations become faster, allowing infinite computational steps in finite time. Consciousness could continue forever subjectively, even as external time approaches an end. Highly speculative, current observations suggest expansion continues forever, not collapse. But Tipler's work illustrates how time, consciousness, computation interweave. What time means depends on what universe we inhabit. What level of mastery over physical law is achievable? Is time fundamental or emergent? In everyday physics, we take time as given. But in quantum gravity, time might emerge from something more basic. Rovelli talks about thermal time. Time arises from thermodynamics, from coarse-graining quantum states. What we call time is related to our ignorance, not tracking every quantum degree of freedom. At the most fundamental level, no time, just quantum correlations. Time appears when you zoom out, when you consider macroscopic averages, like temperature emerging from molecular motion. Individual molecules don't have temperature. Temperature is statistical. Similarly, time might be statistical. This emergent view might resolve tensions between quantum mechanics and relativity. In quantum mechanics, time is absolute background. In relativity, time is dynamical, part of geometry. These don't fit naturally. Both are successful. So both must be approximations to deeper truth. Barber's timeless physics takes this further. The universe is a vast space of possible configurations. Plutonia, each point represents a complete configuration, but they don't flow. They just are. What we perceive as time is that configurations have structure. Form sequences our minds interpret as flow, like film frames. Each exists independently, static, but projected in sequence, motion appears. Similarly, configurations might form paths. Conscious beings would perceive movement along paths, experiencing time. But from outside, no motion, no flow, just structure. Deeply counterintuitive, time feels real. But many things that feel real are constructs. Color, for instance. No such thing as red in light's fundamental physics, just wavelengths. Our brains interpret certain wavelengths as red. Color is in perception, not light itself. Barber suggests time is similar. Perceptual construct from physical reality structure. If right, time travel paradoxes dissolve. No flow to disrupt. You can't change the past because past and future are just different regions. All exist equally. You could access different regions, experience them in unusual orders, but not alter them. The structure is what it is. Timelessly, but this creates puzzles. If everything exists timelessly, what determines which configurations connect into our universe's history? Barber has answers involving quantum mechanics, but they're complex, not universally accepted. Information and time. Information theory developed by Claude Shannon gives tools for quantifying information. Deep connection between information and entropy. Erasing information requires dissipating energy. Increasing entropy. Minimum energetic cost to computation. Tied to second law, times arrow, entropy increase, is connected to information processing. Every memory formation increases universe entropy slightly. Neural changes in coding memory are irreversible. Dissipate heat, consciousness, constant information processing, is entropy generating. We are beings made of increasing entropy. Surfing the second law, if you traveled backward, what happens to memories? Would they persist, violating thermodynamics, or erase themselves as you go backward? You'd arrive with no future knowledge. The latter seems more consistent, but it would make time travel pointless. You wouldn't know you'd travel unless information can be preserved without violating thermodynamics, maybe encoded in quantum states, or in many worlds, traveling to a new branch where thermodynamics starts fresh. These are speculations, but they illustrate how thinking about time travel forces confronting deep questions. The holographic principle, information in a volume encoded on its boundary, from studying black holes. Bekenstein showed black hole entropy is proportional to event horizon area, not volume. Surprising, you'd expect volume scaling. Susskind and Hooft generalized, proposing the universe might be holographic. Information about what happens inside a region might be encoded on its boundary. If correct, three-dimensional space might be a projection from two-dimensional information. We'd be living in a hologram. For time travel, if all events information is encoded on boundaries, perhaps entire history is accessible from that boundary. You wouldn't physically travel through time. You decode holographic information corresponding to different moments. Very speculative, but suggests the past might not be gone, rather encoded in space-time structure, potentially accessible. Quantum entanglement offers possibilities. Entangled particles share quantum state instantaneously across any distance. Einstein was troubled, felt it violated locality, but experiments confirm it's real. Some physicists proposed entanglement might relate to space-time geometry. The ER equals EPR conjecture. Entangled particles might be connected by tiny wormholes. If true, space-time might be stitched together by quantum connections. These connections might provide pathways bypassing normal space-time separation. Could you use entanglement for time travel? Probably not directly. You can't transmit information faster than light. using entanglement alone. But perhaps combined with other effects, entanglement could play a role in mechanisms we haven't imagined. Whether constants of nature vary over time, speed of light, gravity strength, particle masses, we assume they're constant. Same everywhere and everywhen. But some observations hint certain constants might have been different in early universe. The fine structure constant might have varied by tiny amounts over billions of years. If constants change, then time's nature might differ in different eras. Early universe with different laws might have allowed phenomena impossible now. Perhaps time travel was easier then, or will become easier in far future. Laws of physics as we know them might be local in time, valid in our epoch, different elsewhere in cosmic history. I think about explorers who sailed to distant lands, encountering environments unlike anything known, deep ocean, polar regions. Each required new understanding, new adaptations. Time travel might be like that. Not just a journey to different when, but to a regime where rules are different, where intuitions fail. Perhaps that's the real frontier. Not space, but time itself. We've sent probes everywhere in the solar system, peered back nearly to the universe's beginning, but we've barely scratched time's surface, experiencing it only in forward flow at normal rates. What wonders might await in other directions? Backward paths, sideways branches, loops and tangles mathematics suggest could exist. Or perhaps time travel remains forever impossible. A tantalizing mathematical possibility nature vetoes through some principle we don't understand. Perhaps we're meant to be temporal beings, locked into experiencing moments in sequence, unable to revisit or preview. There might be wisdom in that limitation, a reason woven into reality itself. Still, questioning matters, attempting to understand matters. Every time we probe time's nature, we learn something profound about existence, about causality and consciousness and universe structure. Whether or not we build a time machine, the journey of trying to understand whether it's possible takes us to the deepest truths physics offers. Free will becomes acute with time travel. In normal timeline, one flowing forward, we maintain the illusion our choices matter, that we're deciding between possible futures, but introduce time travel, this illusion becomes harder to sustain. If future events can influence past decisions, if closed time-like curves mean what will happen has already happened, where does choice fit? John Wheeler had a participatory view. Observers don't just witness reality. They help bring it into being through observations and choices. In quantum mechanics, before measurement, a particle exists in superposition. Measurement collapses this into definite outcome. You, the observer, participate in creating reality you observe. Applied to cosmology, Wheeler proposed participatory anthropic principle. Observers in present might be necessary to give meaning to past, collapsing the early universe's wave function retroactively through our observations. Radical idea, suggesting consciousness and choice aren't just passive phenomena emerging from physics, but active ingredients shaping reality. If true, perhaps free will survives even with time travel, because choices genuinely create outcomes rather than revealing predetermined results. But not everyone agrees. Many physicists prefer interpretations not giving observers special status, where wave function never collapses, or collapse is artifact of decoherence. In these views, reality is objective and deterministic. Our sense of choosing is of all perception rather than fundamental feature. Compatibilism in philosophy tries reconciling free will with determinism, redefining what free will means. You have free will not in the sense actions are uncaused, but they arise from your desires, beliefs, reasoning, rather than external compulsion. Even in deterministic universe, or one with closed time-like curves, you'd still have free will in this compatibilist sense, because your choices would still be yours, still flow from who you are. I find something satisfying about this view, though I'm not sure it captures what we mean by free will in everyday experience. When you deliberate about a decision, it genuinely feels like the future is open, like multiple possibilities exist and you're selecting among them. Compatibilism says this feeling is real enough. It doesn't matter whether the selection was determined by prior causes, as long as those causes include your own mental processes. Maybe that's sufficient. Maybe we don't need metaphysical freedom, only psychological freedom. Time travel forces these issues into sharp relief. It makes determinism explicit. If you meet your future self, then clearly your future is fixed, at least in broad strokes. You'll become that person, do the things they remember doing. Yet moment to moment, you still experience choosing, deliberating. So which is real? The fixedness or the freedom? Perhaps both. In different senses, perhaps the timeline is fixed when viewed from outside time, from Platonia's perspective of the block universe, but experienced as open when lived from within. This is the tenseless view of time versus the tensed view. Tenseless says all moments are equally real. Past, present, future. Tensed says only the present is real. Past no longer exists. Future doesn't exist yet. We experience time in tensed way, but physics increasingly suggests tenseless view is correct. Let me talk about causal loops in nature. Instances where we see something like circular causation, even without time travel. In quantum mechanics, you can have situations where A influences B and B influences A simultaneously through entanglement. Causal structure becomes cyclic when you look from certain perspectives. These aren't time travel loops exactly, but they show nature already has resources for nonlinear causation we're only beginning to understand. There are feedback loops in complex systems, ecosystems, economies, neural networks, where effects circle back to influence causes. A forest fire creates conditions making future fires more likely. Economic inflation causes wage demands, causing more inflation. Neural activity creates patterns reinforcing themselves. These aren't violations of causality, but they show how causes and effects can interweave in complicated ways. Not simple linear chain. When we think about time travel, we might be too focused on simple cases. The grandfather paradox and such. Real causation in complex systems is messy, full of feedback and circular influences. Perhaps time travel, if it exists, would create causal structures that look similarly messy, difficult to analyze, but not actually paradoxical. Maybe the universe is robust enough to handle these complications, absorbing them into overall consistency without breaking. There's a concept in mathematics called fixed point theorems. These say under certain conditions, a function must have a point where it maps to itself. Where f(x) equals x, the Novikov self-consistency principle is essentially a fixed point requirement for time travel. The timeline must be consistent with itself, must be its own fixed point in configuration space. Mathematical fixed point theorems guarantee such solutions exist under broad conditions, which suggests consistent time travel timelines are possible mathematically, even if physically creating them is impossibly difficult. David Deutsch has applied quantum computation theory to time travel. He's shown that quantum computers in the presence of closed time-like curves would have extraordinary computational power, able to solve problems intractable for normal quantum computers. Essentially, you could send information back in time to help solve a problem, using the answer to generate the answer in a self-consistent loop. It's like looking up the answer in the back of the book, except you're the one who wrote the book using knowledge from the future. This doesn't violate physics. Strangely enough, the computation finds a fixed point where the information loop is self-consistent. There's a unique solution making the loop work, and the quantum computer naturally evolves toward that solution. Deutsch proposed experiments to test this using simulated closed time-like curves in quantum systems. Some initial experiments have been performed. They confirm basic predictions. Though these aren't actual time travel, just quantum systems engineered to behave mathematically as if they were. The implications are stunning. If this scales up, a civilization with access to closed time-like curves could solve problems instantly that would otherwise take longer than the universe's age. They could factor enormous numbers, break any encryption, simulate complex systems perfectly. They'd have computational omniscience within physical law's bounds. Of course, they'd still be constrained by consistency requirements. They couldn't solve logically impossible problems or create true paradoxes. But within those constraints, their power would be godlike. I wonder sometimes whether the universe itself might be doing something like this. Quantum mechanics involves summing over all paths a particle could take, all possible histories. What if the universe is computing its own evolution by exploring all possibilities and finding the consistent solution? Time wouldn't flow in simple linear way, but would emerge from timeless computation, finding self-consistent structure. This is vague, I know. More poetry than physics. But it gestures at possibilities we might not have words for yet. The Wheeler-DeWitt equation in quantum cosmology attempts to describe the wave function of the entire universe. Remarkably, time doesn't appear in this equation. It's timeless. describing a timeless state. Time emerges somehow from quantum correlations within this state, from how different parts of the universal wave function relate to each other. Solving Wheeler-DeWitt fully is beyond our current mathematical ability, but its existence suggests time might not be fundamental even in quantum mechanics when applied to universe as a whole. If time emerges, then perhaps it emerges differently in different contexts or regimes. Perhaps in black hole interiors or at the Big Bang singularity, time doesn't emerge in usual way, and we get structures that seem paradoxical from our perspective, but are natural in that regime. Perhaps time travel isn't really travel at all, but access to regions where time has different structure, where usual rules don't apply because they were always approximations valid only in particular circumstances. This brings me to a subtle point about language and concepts. We use words like travel and past and future that carry implicit assumptions about how time works. When we try describing scenarios where time works differently, we're handicapped by language designed for normal temporal experience. It's like trying to describe color to someone who's never seen, or music to someone who's never heard. The concepts don't quite fit. Physics often runs into this problem. Quantum superposition, entanglement, curved space-time, extra dimensions. These are all things without good analogies in everyday experience. We use metaphors in mathematics, but metaphors are always slightly wrong. And mathematics, while precise, doesn't give intuitive understanding. Time travel might be similar, something that could be described mathematically, but never quite captured in words or mental images that feel right. Perhaps future humans or artificial intelligences or whatever comes after us will think about time in ways we can't currently imagine. They might have cognitive structures or computational frameworks that make time travel seem natural, obvious even. They might look back at our confusion the way we look back at ancient peoples confused by basic mechanics or chemistry. Not because they were stupid, but because they lacked conceptual tools to think clearly about phenomena outside their experience. Or perhaps time travel will remain forever confusing, a phenomenon that can't be domesticated into intuition no matter how much we study it. Some things in physics are like that. Quantum mechanics has been around for a century. Physicists still argue about what it means, how to interpret the mathematics. The formalism works perfectly. Predictions match experiments to extraordinary precision. But underlying reality remains obscure. Time travel might be the same, technically possible perhaps, but never truly understood. There's a curious asymmetry in how we think about space versus time. We accept readily that we can move freely through space, forward and backward, left and right, up and down. No one finds this paradoxical or mysterious. But time, we can only move through in one direction. At one rate, we're trapped in the flow, swept along from past to future at 1 second per second. Why should time be so different from space? After all, relativity tells us they're unified into space-time, that they're aspects of the same underlying structure. The answer, as I've mentioned, seems to lie in thermodynamics, in entropy and the arrow of time. Space doesn't have an arrow. There's no thermodynamic principle favoring north over south or up over down. But time does have an arrow, globally at least. Because the universe started in low entropy state and is evolving toward higher entropy, this asymmetry, this directionality in time, makes it fundamentally different from space in terms of our experience and our physics. But locally, in small regions and short time scales, the arrow of time can become ambiguous. If you film molecules in a gas for a microsecond, you couldn't tell if the film was running forward or backward. The molecular dynamics are time symmetric. It's only over longer periods as entropy increases statistically that direction becomes clear. So there might be regimes, extreme conditions, where the arrow of time is weak or absent, where time becomes more space-like, and perhaps in those regimes, movement through time could be less constrained. Inside black holes, for instance, the roles of time and space swap in a sense. Outside a black hole, you can stay at the same spatial location by applying thrust, fighting gravity, but you can't help moving forward in time. Inside the event horizon, according to mathematics, you can't stay at the same radial position no matter how much thrust you apply. You inevitably move inward towards singularity, but the time coordinate becomes space-like. Does this mean you could move backward in time inside a black hole? The mathematics is ambiguous, and we can't observe it directly, so we don't know. Kip Thorne and others have explored these internal geometries extensively. The rotating Kerr black hole has even more complex interior structure, with ring singularities in regions where closed time-like curves might exist. But tidal forces would be lethal, and geometry might be unstable, collapsing before you could exploit it. Still, the mathematics permits these structures, which means nature at least contemplates the possibility of such exotic space-time geometries. I think about the courage it would take to test time travel if we ever developed the technology. You'd be volunteering to be the first person to violate causality as we understand it, to potentially create or encounter a paradox. Even if theory said it was safe, said consistency would be maintained, would you trust that? Would you step into a wormhole or closed time-like curve, not knowing for certain what would emerge on the other side, or whether you'd emerge at all? Early astronauts had similar courage. They climbed into rockets built by the lowest bidder, as the saying goes, knowing many test flights had exploded, knowing the risks, but time travel would be different. It wouldn't just be your life at risk, but potentially causality itself, the logical structure of reality. A malfunction wouldn't just kill you, it might create a paradox that, well, we don't know what would happen. Would the universe prevent it? Would you create a new timeline? Would reality somehow glitch or break? The consequences of failure are literally impossible to predict. Maybe that's why, if time travel is possible, we haven't seen travelers from the future. Maybe every civilization that develops the technology is simply too cautious to use it. Or they use it once, something goes wrong, and in that timeline, they cease to exist or lose the ability to try again. We might be in a timeline where time travel is never successfully deployed. Even though it's theoretically possible, the successful deployments happen in other branches of the multiverse that we can't access or observe. There's also the possibility that time travelers are here among us. But undetected, if you travel to the past, you'd want to be subtle. To observe without interfering, you dress in period clothing, adopt period mannerisms, blend in. Maybe people we think of as eccentric geniuses or uncanny predictors were actually time travelers with knowledge of the future. Leonardo da Vinci, sketching helicopters and submarines centuries before they were built. Nostradamus making predictions that seem remarkably accurate in retrospect. Maybe, or maybe not. These are fun speculations, but there's no evidence for them, and they require conspiracy-level thinking to sustain. The simpler explanation is that genius exists, that people can be ahead of their time through intelligence and imagination alone, without literal time travel. We should be skeptical of extraordinary claims without extraordinary evidence. Still, the idea captures something important about how we think about time and knowledge. We wish we could see the future or change the past. It's a deep human desire reflected in countless myths and stories. The Oracle at Delphi seeing the future, Orpheus trying to retrieve Eurydice from the underworld of the past. The ability to transcend temporal limitations is portrayed as divine, as beyond human capability. And maybe it is. Maybe time travel remains in the realm of gods and myths because that's where it belongs, beyond the reach of physical law. But I'm not ready to accept that yet. Physics has surprised us too many times, revealed possibilities we never imagined. A century and a half ago, physicists thought they'd figured everything out, that only minor details remained. Then came relativity and quantum mechanics, and the universe turned out to be far stranger than anyone had dreamed. We're likely still in similar position. We know some things, but there are vast territories of ignorance remaining, especially around quantum gravity and the deepest nature of space-time. When we finally have a theory of everything, or at least a theory of quantum gravity unifying general relativity and quantum mechanics, it might tell us definitively about time travel. It might say, yes, here's how it works, here are the rules. Or it might say, no, here's why it's impossible, here's the principle that forbids it. Either answer would be profound. Either answer would teach us something fundamental about the universe. Until then, we're in this strange liminal space where time travel is possible mathematically but implausible practically. Permitted by equations but perhaps forbidden by some deeper principle we haven't discovered. It's a space of uncertainty, of wonder, of possibility. And in some ways, that's more exciting than knowing for sure. The question remains open. And open questions are what drive science forward. Let me tell you about one more theoretical proposal, one that's particularly elegant. The Roman ring, proposed by Thomas Roman. Imagine an ordinary cosmic string formed into a closed loop. A ring. The geometry of space-time around this ring has interesting properties. If you travel around the ring in a particular way, you can return to your starting point slightly earlier than you left. It's a very small effect, fractions of a second. But it's a closed time-like curve. What's elegant about the Roman ring is that it doesn't require exotic matter or negative energy. It's just geometry, the natural curvature of space-time around a massive ring. Of course, creating a cosmic string ring would require control over physics at energy scales comparable to the Big Bang. So it's not exactly practical, but it shows that time travel might not always require exotic ingredients. Just extreme conditions and precise arrangements of normal matter energy. It makes me wonder what other solutions to Einstein's equations we haven't found yet. The equations are notoriously difficult to solve in full generality. Most solutions are highly symmetric, simplified cases that make the math tractable. But the universe isn't fully symmetric. Real space-time is lumpy, irregular, full of stars and galaxies and complex structure. Maybe in some of these irregular configurations, there are natural closed time-like curves or wormholes that form spontaneously under the right conditions. Astronomers sometimes find objects that don't quite fit our models, anomalies in the data that take years to explain. Usually, they turn out to be unusual but not inexplicable phenomena. But occasionally, they point to something new. Pulsars were initially mysterious, regular radio signals that seemed almost artificial. They turned out to be rotating neutron stars, predicted theoretically, but not yet observed. Could there be similar surprises hiding in the data? Signatures of exotic space-time geometries that we haven't recognized because we don't know what to look for? The search for gravitational waves has opened a new window on the universe. LIGO and Virgo detect ripples in space-time from violent cosmic events. They've seen black holes colliding, neutron stars merging. As detectors become more sensitive, they'll see more subtle phenomena. Could they detect signatures of wormholes or time loops if they exist? Perhaps the gravitational wave signature would be distinctive. Different from known sources? It's worth looking, even if chances are small. I'm reminded of a quote from Arthur C. Clarke. Any sufficiently advanced technology is indistinguishable from magic. Time travel would certainly seem like magic to earlier generations, and perhaps even to us. But it might not be magic. Just engineering we don't yet know how to do. Physics we don't yet fully understand. The line between possible and impossible isn't always clear, and it shifts as knowledge grows. You know, as we reach the end of this journey through time travel, paradoxes, and possibilities, I find myself thinking about what it all means for us here and now. We've explored wormholes and closed time-like curves, grandfather paradoxes, and many worlds interpretations. The nature of causality and consciousness. We've touched on quantum mechanics and general relativity, thermodynamics and cosmology. And through it all, there's been this persistent question: can we transcend time, or are we forever bound to its linear flow? Perhaps the answer doesn't matter as much as the asking. The fact that we can conceive of time travel, that we can use mathematics and physics to explore its possibilities and paradoxes. This tells us something profound about human consciousness. We're not content with the world as it presents itself. We imagine alternatives. We probe boundaries. We ask, what if? This capacity for imagination, for extending our minds beyond immediate experience, is perhaps more remarkable than any time machine we might build. When you think about it, we already are time travelers in a limited sense. Every moment we move from past to future. We carry memories of what was. We make plans for what might be. Our consciousness spans time in a way other processes don't. A rock exists in the present moment only. But you exist across time, connected to your past selves through memory, to your future selves through anticipation. You are a temporally extended being, a four-dimensional structure moving through space-time. And we have methods, crude but real, of influencing the future and preserving the past. We write, we record, we create artifacts that outlast us. These are messages to the future. Our attempt to reach across time and speak to people who don't yet exist. Every book, every photograph, every recorded song is a form of time travel, carrying information from past into future. When you read Shakespeare or Homer, you're receiving thoughts from minds centuries dead, preserved through time by marks on paper or screen. We also preserve the past in our very bodies and minds. Your DNA carries information from ancestors stretching back millions of years, billions even, to the origin of life itself. The structure of your brain was shaped by evolution, by experiences of countless generations, solving problems and adapting to environments long vanished. You are, in very real sense, a message from the deep past, a continuation of patterns that have persisted through geological ages. Every heartbeat, every breath, every thought is part of that ancient pattern evolved across time. The future, too, lives in us. Our actions shape what will be. The choices we make ripple forward, influencing events long after we're gone. Scientists working today might enable discoveries centuries hence. Artists create works that will move people not yet born. Teachers shape minds that will shape the world. We can't visit the future, but we build it moment by moment, choice by choice. That's a kind of power over time, modest but real. I suppose what strikes me most about time travel paradoxes is how they force us to confront the structure of reality itself. Are we free or determined? Is the universe fundamentally random or ordered? Does consciousness play a special role in physics? Or are we just complex arrangements of particles obeying impersonal laws? These aren't just abstract philosophical questions. They affect how we understand ourselves, how we make decisions, how we find meaning. If time travel were possible, if you could visit your past self or see your future, what would you say? What would you change? The question is almost painful because it reveals regrets and hopes we carry. We wish we'd made different choices, taken different paths. We wonder anxiously about outcomes not yet determined. This emotional weight we attach to time, to past and future, is part of what makes us human. We exist not just in the moment, but across time, haunted by what was and drawn toward what might be. The paradoxes reveal something about identity and causation, about what makes things the way they are. If you prevent your grandfather from meeting your grandmother, do you cease to exist? The question assumes certain continuity of identity, that you are fundamentally the same person across time. But maybe that's not quite right. Maybe the you of today is already different from the you of yesterday, connected by memory and physical continuity, but not identical. Maybe identity is more fluid than we think. And paradoxes arise from treating it as rigid. Some Buddhist philosophies hold that the self is an illusion, that there's no persistent essence constituting you across time. You are a process, a pattern of change, not a thing. If that's true, then time travel paradoxes become less troubling, because there's no fixed self to preserve or contradict. The pattern could loop or branch or tangle, and it would still be valid as a pattern, still meaningful even without classical identity. I'm not saying this is correct, just that different ways of thinking about identity and time lead to different intuitions about paradoxes. What physics has taught us again and again is that our intuitions aren't always reliable guides to reality. The universe is under no obligation to make sense to evolved primates on a small planet. We've had to stretch our minds, develop new mathematics, new conceptual framework to understand even a fraction of what's out there. And we're probably still missing vast territories of understanding. Phenomena we can't even conceive of yet because we lack the concepts. Time travel might be one of those things requiring concepts we haven't developed. Or it might be simpler than we think. Once we understand quantum gravity and the deep structure of space-time, we won't know until we get there, until someone derives the right equations and checks them against observation. That's the beauty of science. It surprises us. It takes us places we didn't expect to go. I find something peaceful in the idea that all moments in time exist equally, that the block universe is real. It means nothing is truly lost. The past still exists, just at different coordinate in space-time. Everyone who ever lived still exists in their moment, still real in four-dimensional structure. And the future already exists too, waiting for us to reach it. We're not creating time as we go, but discovering it, revealing what already is. There's a timelessness to this picture, an eternal quality that's comforting somehow. But maybe it's not true. Maybe only the present exists, and we genuinely create the future through our choices. Maybe time is an open frontier, and we're pioneers moving into it, shaping it as we go. That's empowering in a different way, suggesting our actions truly matter, that we're building reality rather than just uncovering it. I don't know which picture is correct, or if either is. Perhaps the question is ill-posed, based on categories that don't map cleanly onto reality. What I do know is that time is precious, We experience it, whatever its ultimate nature, as finite and irreplaceable. Each moment passes and doesn't return, or at least we can't return to it. This creates urgency, poignancy, beauty. If we could revisit any moment infinitely, would moments matter as much? Would we treasure experiences if we could repeat them endlessly? Maybe limitation is what gives time its value, what makes life meaningful. If we ever achieve time travel, I hope we use it wisely, with reverence for causality and history. I hope we don't treat the past as a playground to be altered on whim, or the future as a resource to be exploited. Time, in all its mystery, deserves respect. We are creatures of time, shaped by it, defined by it in fundamental ways. To transcend it completely might be to lose something essential about what we are, but to understand it better, to probe its secrets, to learn whether closed time-like curves are possible or forbidden, whether many worlds, branch, or timelines stay fixed, whether consciousness plays a role or is just a passenger. These pursuits are noble, beautiful, even. They push us to limits of imagination and mathematics. They force us to question assumptions we didn't know we were making. And in the process, we learn about ourselves, about how we think, what we value, what we fear. So thank you for joining me on this journey through the paradoxes and possibilities of time travel. We've covered enormous ground, from Einstein's equations to quantum entanglement, from wormholes to cosmic strings, from thermodynamics to consciousness. We've asked difficult questions and found that answers are often more questions, deeper and stranger than what we started with. That's the nature of fundamental physics. Each answer reveals new mysteries, new horizons to explore. As you drift off to sleep now, maybe you can imagine yourself as a time traveler of sorts, moving through the night toward tomorrow. Your consciousness will pause, will go quiet for a while, and when it resumes, hours will have passed that you didn't experience. Sleep is its own kind of time travel, a gap in awareness that carries you forward without the journey. And in dreams, time becomes fluid, elastic, sometimes flowing backward or looping or branching in ways that defy normal causality. Perhaps dreams are the closest we come to experiencing nonlinear time, where past and future mix, where impossible things happen without paradox. The dreaming mind doesn't worry about consistency or causation. It simply creates moment by moment experiences that don't obey waking logic. Maybe that's worth contemplating as you fall asleep. This nightly journey into a realm where time works differently. Rest well and know that the universe is vast and strange and full of wonders we're only beginning to understand. Time travel may or may not be possible, but the fact that we can ask the question, that we can explore it mathematically and philosophically, that is itself a kind of miracle. Sleep now. And perhaps tomorrow will bring new insights, new perspectives, new ways of thinking about these ancient questions, about time and existence and our place in the cosmic story. Good night, and safe travels through whatever mysteries await in sleep and in waking.